Hello everyone, welcome back to part 2 of lecture 15. So we were discussing about the different types of channel planform. Now we will continue this with the meandering river, right? So a meander is one of a series of regular sinus curves, bends, loops, turns or winding in the channel of a river, stream or other water course, right. It is produced by a stream or river swinging from side to side as it flows across its floodplain. So here you can see how it is happening. So the transformation of a straight channel with a ripple pool bed into meandering channel. This is from Keller 1972. So here you can see the stage 1, stage 2, stage 3, stage 4 and stage 5, how a straight channel is becoming the meandering channel, right. Then comes the braided river. A braided river or braided channel consists of a network of river channels separated by small and often temporary islands called braid bars. So these braid bars can be easily seen in the non-monsoon period, right. Lane in 1957 concluded that there are two primary causes of braiding. Why this braiding is happening, right. So the first one is overloading. A stream may be supplied with more sediment than it can carry and hence some may be deposited. Then steep slope, it causes a wide shallow stream in which bars and islands may readily form. So here you can see the mechanism of braid development and this is from this particular paper. So mainly the braiding, the braid bars are generated because of the two reasons. The first one is the overloading and the second one is the steep slope. So Lockton postulated that river forms reflect three main independent factors, right. So this is very important. So here you can see this particular diagram explains three main characteristics, right. So the discharge which depends on climatic and soil condition. So this will be here. Slope or gradient conditioned by the relief of the area crossed by the river. So the bed slope. Then comes the erodibility of the bed depending upon the sediment properties. What kind of sediments are present in this water, that will decide and that will actually cause this erosion, right. These three controls determine features of the river and hydraulic condition of the flow. So these three are very important. So when we talk about the stream power, we all know that we can quantify it using this equation. So Lockton offered a channel development criteria defined as the ratio between the stream power and the erodibility of the bed. Lower value of this particular ratio says stable sinus, that is meandering river, and higher values confirms to unstable divided or braided stream. So this ratio is very important. Braided rivers as distinct from meandering river occurs when a threshold level of sediment load or slope is reached while a steep gradient is also maintained. In 1957, both Leopold and Wollman and Lane published the result of channel pattern analysis using gradient discharge chart. So here you can see this is different structure level. So the valley bottom, flood channel and then low water channel. So here you have straight, sinus and branched, and here the limiting conditions are wide flood plain. The limiting conditions are wide flood plains, confined channel and incised channel, right. And here you can see all these different characteristics. So this is the major type of channel planform and it is nicely representing all the planforms. Now let us see the QS diagram. So Romasin in 1968 constructed a QS diagram using valley slope and median flood discharge for freely developing channels. So, this annual flood valley slope diagram for different channel pattern can be seen here. Analyzing this diagram, then again it was suggested, considering stream power per unit of flow length, that is omega is equal to rho g QS, right, and the unit is watt per meter. He found some omega threshold between free meandering, incomplete meandering and multi-branching pattern. And after re-examination of the data in terms of a modern classification, the field of the diagram may be divided into three parts. The first part is area of meandering, that omega is less than 4. Second one is area of meandering and branching, that lies between 4 to 15, and the area of branching, that is greater than 15, right. So, this is the further advancement in the QS diagram. Annual flood channel slope diagram for different bar level classifications can be seen here. So, the y axis is flood channel slope and x axis is the effective discharge. So, they demonstrated that braided river plot above meandering ones, straight channels are plotted either on both sides of the meandering braided transition or below the meandering channel, right. Any slope over this threshold created a braided stream, while any slope under the threshold created a meandering stream, or for very low slope a straight channel. So, the main controlling factor on river development is the amount of sediment that the river carries. Once a given system crosses a threshold value for sediment load, it will convert from a meandering system to a braided system, right. Now, let us talk about the parameters which represents the planform, right. So, how to evaluate the planform. So, the parametric evaluation will be discussed now. So, you can see the first one is the sinuosity index, then braiding index, braid channel ratio, then comes the channel width and then bank line shift. So, this sinus represents the meandering and curvy nature, braided represents the formation of islands or bars. So, if you remember this, you will not have any confusion in different types of planform. Sinuosity index refers to the ability of flowing water to form bends, right. So, this is basically we are evaluating how it is bending, right. So, the sinuosity index can be calculated using this, and here what we do is we try to take the channel length. So, let us say this is the main channel of this particular river. So, this distance is 600 meters, right, and the valley length, the straight distance between the starting and ending. So, this is coming around 400 meter. So, this is what is used in this sinuosity index. So, here you can see that sinuosity values ranges from 1 to 4 and channels can be termed as straight, sinus or meandering based on this sinuosity index. So, here if the value is less than 1.1, it is straight. If the value is between 1.1 and 1.5, then it is sinus, and if the ratio is greater than 1.5, then it is meandering. So, using this you can identify what type of river system you are looking at, right. So, this is the same example I am using here to calculate the sinuosity index. So, earlier if you remember we had the valley length and the channel length. So, the main channel length and then we had the valley length of 400. So, this is coming 1.5 which is here. So, this is sinus. So, this is sinus river, right. Few other sinuosity indices are also available. So, here this is the one, here length of links and the reach length that is used. Here length of links and length of main channel links that is used to calculate. So, these are two different methods other than the previous one. Now, let us see the braiding index. So, it allows comparison between different channel reaches and can be used to assess channel changes over time. The braiding index can be calculated using this equation. So, here we are using mid channel length of widest channel in the reach, and then we are using sum of mid channel length of all the segments of primary channels in a reach, right. So, here you can see that LC total and LC max, how it is being used. So, this defines the braiding pattern. The ratio BR, the braiding index, is a measure of the tendency of the channel belt to develop multiple channels in a reach, right. If the reach has a single channel, BR will be unity where BR is greater than 1, that indicates a braided river, and a higher BR value implies a higher braided river system, right. So, here you can see the braiding index and braiding index value. So, this is 2.4. So, if the value is higher, then it is having higher tendency to braid, right. Bar island indices. So, this is from Bryce, and here you can see the length of islands or bar and the reach length that is used, and here you can see the length of islands or bars, reach length and total number of bars that is also used, right. So, this is bar or island indices. Some other indices are also available. So, here you can see, then comes the channel count index. So, this is given by Howard et al. 1970 and Hong and Device 1979. So, here they are using the cross section area, mean number of links per axis or reaches, right. So, now you must be comfortable how to extract these information which is required to quantify these values, because we have learned the remote sensing data sets can be downloaded and then it can be used to generate these information, the cross section length, valley length, water flowing length. So, all these values can be generated. Now, let us see the bank line migration study. The spatiotemporal variation of the geomorphology predicts the future trajectory of channel planform and its vulnerable zones, because this spatiotemporal, that over the time how this particular river is behaving, that will help you to predict what will happen in the future, right. This Flashy river is characterized by a large sediment load generated from the Himalayas. This is from Kaming, this is Kaming river, right, which forces the river to change its flow pattern and channel morphology. The downstream section of Kaming river has been subjected to channel migration for the last 40 years, which has generated severe bank erosion problem. If you remember, when I was showing you the summary for Ganga, Brahmaputra and Mahanadi, the Brahmaputra has the major problem of the bank erosion, right. So, you can see here the 1988 remote sensing data, it helped us to demarcate the boundary of the river. Then with respect to 1988, how this Kaming river is shifting, right, how it is changing its course. So, in 1992, this is with this orange color, right. So, how it has been shifted. So, sometimes only one bank is shifting, sometimes both the banks are shifting, sometimes the width is changing. So, that kind of analysis you can perform using this remote sensing data. Now, when you see 1988 and 1997, then in 2002, so that will help you to analyze what is happening with your river system that you are interested to study, right. So, in this study, we tried to understand the morphodynamic of calming river between 1988 to 2022 with remote sensing data, field investigation and some cloud computing techniques were used. The Landsat satellite imagery from USGS that were used and then processed to evaluate the annual bank migration rate. The right and left bank, I will be showing you the graph. So, the right and the left bank are digitized manually and this process has been carried out carefully by marking the external boundaries of the bank attached geomorphic units. So, this can be done automatically also, but we thought of doing it manually because we also have done this automatically, but manually we have more confidence on our results, right. So, the study area is divided into 47 and 23 segments in the hilly and the plain reaches respectively. The segments are spaced at an approximate interval of 1 kilometer, which can effectively capture the morphological variation of bank attached geomorphic units. Now, you will be able to perceive this what I have already discussed. So, this is the calming river and here you can see how these reaches are designed, right. So, it is approximately at 1 kilometer. So, this is the hilly part and this is the low lying areas, right, and then it is meeting the main Brahmaputra river. So, here you can see the migration rate we have analyzed and the segment number is also given, and here you can see that this particular reach it is showing negative, right. So, this you can see the color. So, this is 15 number and this color is here. So, between this time period there is a change in the bank line. The migration of the bank between certain time period is measured at every point by overlaying the digitized image of the bank lines. Inward movement of the bank line is considered as deposition. So, this is the inward, right, and outward movement of the bank lines as erosion. If it is going this side, then it is erosion. The negative and positive notations are adopted for deposition and erosion respectively. So, this is how we have analyzed the whole calming river system, right. So, right bank migration you can see here, this is for the left bank. So, again the negative values are for the deposition, positive values are for the erosion, right. So, here this is the bank erosion you can see, right. So, this is how you can analyze the bank line shift or bank line migration. In the hilly region, the river passes through valley confinement and therefore, the bank migration rate is minor and close to 1 to 2 meter per year. At a few upstream reaches of part 1, that hilly areas, the river has abandoned the old flood channels and depositional behavior is observed. At segment number 15 of part 1, a deposition rate of close to 400 meter per year is observed due to the shifting of the primary channel between 2014 and 2016. The maximum erosion rate is generally witnessed at the junction of hill and plain section. So, this is 30 to 40 reach number. The erosion prone reaches are segment 33, 35 and 36 between 2014 and 16, segment 46 in 10 to 14 and segment 33, 34, 38, 39 and 43 between 2002 and 2010. At present 2016 to 2022, the spatial averaged bank erosion rate is close to -4 meter per year, which shows the gradual emergence of bank protection work and stability character in the upper Jiyabarali river. So, In the plain region, the Guwahati river is dynamic in terms of bank line migration, breeding behavior and geomorphic adjustment. In the first time period 1988 to 1992, the river had a spatial averaged bank migration rate of 77 meter per year, with the highest bank erosion rate of 378 meter per year at segment number 19 to 21. This is in the lower reaches, right. In the next epoch, that 1992 to 1997, the spatial averaged bank migration rate of 24 meter per year with a maximum erosion rate of 190 meter per year was observed close to segment number 15 and 16. During the next two time period, that is 97 to 2002 and 2002 to 2010, the river continued its westward migration between 7 to 18 reaches, with the right bank subjected to intense erosion and left bank witnessed gradual deposition. At the present epoch, that 16 to 2022, the Guwahati river has an average channel migration rate of 4.25 meter per year, with erosional behavior at the calming Brahmaputra confluence. So, why I am showing you all these result and analysis of my work? Because this kind of analysis can provide you more insight or detailed information about the characteristic of your river, what is its behavior, and then you can go for the modeling of this particular section. Some of the linear aspect that I have listed here. So, stream ordering, and here all the details are given. So, I will not go in detail, but I will just show you, so that if you require, then you can refer to these methods, and I have written the author's name also. This is a compiled work. This is the compilation of all the different indices which are available for morphometric analysis, right. So, you can just take a note of this: drainage frequency, drainage texture, form factor, elongation ratio, drainage density, length of overland flow, texture ratio, basin relief, circularity ratio, constant of channel maintenance, infiltration number, then gradation ratio, ruggedness number, relative relief, and then hypsometric curve. All these methods can be used for the morphometric analysis, and the aspect is relief, right. Then comes the morphotectonic aspects. So, how we identify whether your particular section of the river is tectonically active, right. So, for that we have different methods: valley floor width height ratio, asymmetry factor, transverse topography symmetry, channel sinuosity index, mountain front sinuosity index, lineament density, hypsometric integral, stream gradient index, normalized steepness index, channel steepness index. All these methods can be used to evaluate the morphotectonic aspects of your river system. Here you can find the list of data sets which are used in such studies. So, we have series of Landsat, series of Sentinel, and you also have microwave data set in this. Then comes the topography, the digital elevation models which are available from various sources. So, these are popular in these kind of studies. So, this already we have discussed. I hope you will remember this, and then you will be able to utilize this knowledge in your research work. So, this is one of the example from this paper. So, you can see here Landsat 8, Sentinel 2, Sentinel 1 data sets are used, and they are monitoring the same river channel with different data set, and here you can see how this is changing, right. Then dry and wet period, this is from another work, right. And here you can see the false color Sentinel 2 imagery, and for the dry season and wet season, and you can see how the rivers are changing. This is the example of Landsat images used in Google Earth Engine. Visual workflow for extracting active channel from a series of Landsat image in Google Earth Engine. So, this is spatiotemporal analysis. This is another example how it is changing with time. So, you can see the 1989 to 2019 how this is changing, right. This is another example from this paper, and here you can see in 1972, 1999, 2009, and this is the compiled work from 1972 to 2014. So, this is bank line change. The bar erosion and the bar migration can be studied using such data set. This is from the Jamuna evolution. So, here you can see the Ganga and Brahmaputra, the junction that is being studied. So, 1973 to 2014, and the confluence migration that is also studied, right. So, these are some of the examples of application of remote sensing in river planform studies, and people are actively using this satellite images or geospatial technique as a tool which can help you to derive the information required to study the bank line shift or the channel migration, or in particular channel planform, right. So, these are some of the suggested reading that you can go through if you are interested to work in this particular domain, and the next slide will have the references, and these references that I have been using in this particular lecture. So, with this I will end this lecture. Thank you very much.